let's look at an application for the definite integral. What we're going to do is think about what would it look like to find the average value of a function on an interval. Of course, we need to figure out exactly what we mean by that before we can actually write down a definition and use the definition. So to figure out what we might mean by the average value of a function, let's think about how you calculate the average value of a collection of numbers. So if you have a bunch of numbers, which I'm representing just by bars here, maybe something like this, 4 different bars, to calculate the average of these, first thing you do is you add them up. Right, so since these are bars, we could maybe just stack these bars on top of each other like this. So you add them up, and then you divide that result into equal parts based on how many things you started with. So equal parts, how to express that? I guess just say based on how many there were. Okay, so that's how you calculate the average of some numbers. But how would that work for a function on an interval from a to b? Well, if you think about a function like this, how many values does a function have? Well, there's one value here, there's another value here. There are all of these different values. In fact, at every x value between a and b, the function takes a value. So it's as if there are infinitely many vertical line segments here, right? In the discrete case, we had just 4, but here we have infinitely many all packed together between a and b. So we have to be careful about how we add these up. If we just laid all of these line segments end to end, since there are infinitely many line segments, it seems plausible that if you laid them end to end, you would end up with an infinitely long line segment. In this case, you certainly would. So we can't just add up the length of these line segments. That doesn't really make any sense. What else could we do? We have to come up with some other way of what it means to add them up. Well, maybe instead of adding up their length, we should add up their area. But what do you get if you add up the area of all of these line segments? You get the area of the whole region. That's just the integral from a to b. So for the function case, or the continuous case, instead of adding up individual numbers, we should compute an integral from a to b of f of x dx. Okay, and now we need to somehow divide this into equal parts based on how many things we added together. Well, the number of individual vertical slices in this region is infinity. There are infinitely many slices here, one for every x value between a and b. And it doesn't really make sense to divide this by infinity. You'd get 0 every time, and that's not particularly interesting. But the word many here, this really only makes sense when you're talking about discrete things, like individual separate numbers. When you're talking about continuous things, the right word instead of many is how much. So on the x-axis, how much stuff is there between a and b, just on the x-axis itself? Well, how do you measure distances along the x-axis for an interval? You just subtract the endpoints. So the amount of stuff there is here along the x-axis is b minus a. So what we should do is take our sum and divide it by how much stuff we started with, which was b minus a. And so this is the value that we will define to be the average value of f of x on the interval from a to b. This actually has a really nice interpretation geometrically, which works like this. If you imagine sort of taking this shape, this region, and putting it under a big piston and moving the piston down to squash this region, right? The high points are going to sort of get squashed down into the low points, and you're going to end up with some sort of solid rectangle of area that has the same area as the region you started with, right? We aren't actually changing the area, we're just sort of squashing it so it all gets level on top. The width of this rectangle is b minus a, and the height of this rectangle that you get, turns out it is the average value. So that's sort of geometrically what the average value is. Great, so we have a definition for the average value. Let's actually compute one of these things. So for example, let's suppose that we have a 10 centimeter metal rod, so something like this, and it's 10 centimeters long, and we're going to let x be the distance from one end. So say the left end is x equals 0, and the right end is x equals 10. And the temperature along the rod is changing so that at a distance x from one end, the temperature is given by this formula. What is the average temperature of the rod? Well, the average temperature, right, the x values that we are going to use are from 0 to 10, because those are the x values where we actually have rod. So we just need to find the average temperature from 0 to 10. And we have a formula for that. So it's 1 over the right-hand end of the interval minus the left-hand end of the interval times the integral over that interval. So integral from 0 to 10 of our temperature function, t of x dx. Now all we need to do is calculate this integral. So 1 over 10 times the integral from 0 to 10 of, let's see, x squared minus 8x plus 11 dx. Right, now we can break up this integral over the sums. So we get 1 over 10 times the integral from 0 to 10 of x squared dx minus, also we can move this constant multiple of 8 outside of the integral. So 8 times the integral from 0 to 10 of x dx plus the integral from 0 to 10 of 11 dx. All right. Fortunately, each of these integrals is something that we have a nice way of calculating. So this first integral, integral of x squared, we had a formula for that in the previous video. It's 1/3 times the top bound cubed minus the bottom bound cubed. All right, minus 8 times. Now the integral of x, we had a nice formula for that. It was 1/2 times the top bound squared minus the bottom bound squared, so it's 10 squared minus 0 squared, plus, and then the integral from 0 to 10 of the constant function 11, this is another rectangle. So here we have a constant function with height 11, and we're going from x equals 0 to x equals 10, and this gives us a rectangle that's 11 by 10, and 11 times 10 is 110. All right, now we're done with the calculus. We just need to do some arithmetic here. So 1 over 10, 1/3 times 1,000 minus, these simplify to 4. So 4 times 100, 400 plus 110. So 1/10 times 1,000 over 3 minus, let's see, negative 400 plus 110 is negative 290. While we're at it, we might as well divide by 10 to get rid of this, so that gets rid of those zeros. So we have 100 over 3 minus, let's see, 29 is the same thing as 87 over 3. So 100 over 3 minus 87 over 3 is 13 over 3. So the average temperature of that rod was 13/3 degrees Celsius. So you can see that sort of conceptually an average value is kind of tricky, but now that we have a formula in hand, it's just a matter of calculating a definite integral.